All right, let's get right into it. Today, we're talking about the Therac-25. Now, this was a medical machine designed for a really noble purpose, to save lives. But a tiny, hidden flaw in its programming turned it from a healer into a killer. It's one of the most serious and tragic computer-related accidents in history.
And no, this isn't from some sci-fi horror movie. This is the real, documented story of how a software bug, buried deep inside a radiation therapy machine, had absolutely catastrophic consequences. It's a case study in tech failure that engineers still study, and for a very good reason.
So this is it. This is the machine we're talking about. The Therac-25 was a medical linear accelerator. Back in the early 80s, this was state-of-the-art stuff. Its whole job was to deliver these super precise, targeted doses of radiation to destroy cancer cells. It was supposed to be a symbol of medical progress.
But then, things started going horribly, horribly wrong. Patients started reporting these bizarre and frankly terrifying injuries during their treatments, and it set off this whole mystery that would take years to finally unravel.
I want you to just picture this scene for a second. A patient is getting their treatment, and suddenly they feel this intense, searing pain, like a massive electric shock. They scream out, "You burned me!" The operator, of course, stops the machine, rushes in, but when they look at the computer console, the screen has this calm, green message, verified. It says all the parameters were normal. Treatment complete.
And this is the central conflict, right? Who do you trust? Do you trust the person who is screaming that they are in absolute agony? Or do you trust the sophisticated, multi-million-dollar computer that's insisting everything went perfectly? Well, for way too long, the hospitals and the manufacturer, they trusted the machine. And that trust, it proved to be fatal.
So to really understand how something like this could even happen, we've got to look under the hood. The story of the Therac-25 isn't just about one accident. It's about this fundamental shift in how we design things, where software was given complete and total control over a potentially lethal device. An idea that we live with every single day now, but was pretty radical back then.
At the physical heart of this machine was this component you see here, the turntable. Its whole job was to rotate different parts into the path of an electron beam, and that's how it switched between two very different modes of treatment.
So the machine basically had two main settings. First was a low-power electron mode. This sent a beam of electrons directly to treat tumors right on the surface. Simple enough. But the second was a high-power X-ray mode. And in this mode, the electron beam was about 100 times more intense. It would hit a metal target to create powerful X-rays that could get to deeper tumors. But, and this is the important part, to be safe, that incredibly potent beam had to pass through a special shield called a beam flattener to spread out its energy.
Now, on all the previous machines, like the Therac-6 and the Therac-20, safety was guaranteed by something called hardware interlocks. Just think of these as physical locks, a specific key that has to fit in a specific lock, a mechanical switch, a circuit that physically cannot turn on unless everything is in exactly the right place. They're simple, they're robust, and they are incredibly reliable.
And this is where it all went wrong. With the Therac-25, the manufacturer, a company called AECL, decided to just get rid of those proven hardware interlocks. They thought they were bulky, expensive, so instead they bet everything on software. They put the software in charge of all the safety checks. The machine's entire safety system now depended on one single assumption, that the code was absolutely perfect. So, as the number of accidents grew, investigators were just completely stumped. The machine would deliver this massive overdose, and then, moments later, it would pass every single diagnostic test they ran. It was like they were hunting a ghost. A deadly error that would appear and then just vanish without a trace.
This was their only clue. During an overdose, the screen would flash this message, malfunction 54. And that was it. No warning, no explanation of what that meant. For the operators, it was just another cryptic error that usually meant they just had to restart the treatment.
And here's the truly unbelievable part. There was no way for them to know how dangerous this was. The official user manual didn't even have a list of what the malfunction codes meant. The operators were flying completely blind, with no idea that malfunction 54 was the machine's silent scream that it had just delivered a potentially lethal dose of radiation.
For its part, the manufacturer, AECL, was just convinced their machine was safe. They couldn't make the error happen in their own labs. They told hospitals it was impossible for the Therac-25 to deliver an overdose. They blamed faulty hardware, or even suggested patients were just getting an electric shock. And after every single incident, they gave the all clear, and the machines were put right back into service.
The big breakthrough finally came from a hospital physicist who just refused to give up. He noticed that the accidents only seemed to happen with the experienced operators, the ones who could type really, really fast. So, after hours of practice, he taught himself to enter the treatment data just as quickly as they did. And then he saw it. Malfunction 54. He had finally captured the ghost.
So what did the investigators find in the end? Well, it wasn't just a single mistake. It was a total breakdown of software engineering practices, a cascade of failures that all lined up perfectly to create a digital perfect storm.
The specific bug is something called a race condition. It's a classic and often really dangerous type of software flaw. It happens when two or more parts of a program are supposed to run in a very specific order, but their timing gets all mixed up. The result all depends on which piece of code wins the race, which leads to totally unpredictable and, in this case, catastrophic behavior. Okay, so here is exactly what those fast typing operators were doing. They would select X for X-ray mode, then really quickly use the up arrow key to edit that entry to E for electron mode, and then hit Enter, all within about 8 seconds. This rapid-fire sequence is what triggered the race condition. One part of the software registered the command to fire the high-power X-ray beam, but the physical turntable, which was controlled by a slower part of the software, just didn't have enough time to move into the right position. And the result of that race? Catastrophe. The turntable stayed in the position for the low-power electron mode, which meant that protective beam flattener wasn't in place. But the machine went ahead and fired the full-power, unfiltered X-ray beam, a concentrated blast of energy about 100 times stronger than intended, directly into the patient.
But you see, the race condition wasn't the real cause. It was just a symptom of a much deeper problem with the whole engineering process. The software was just recycled from older machines that had hardware backups. It was written by a single programmer with almost no documentation. And, most damning of all, in ACL's own safety analysis from 1983, they just assumed that software couldn't fail. It wasn't even considered a possibility.
The fallout from the Therac-25 is why it's probably the most famous computer bug in history. This tragedy forced this huge reckoning in software engineering and medical device regulation. It created lessons that were, quite literally, written in radiation. It was the moment the world learned that a software bug isn't just an error on a screen. It can be lethal.
And this timeline just shows how slow the response really was. For 2 full years, from 85 to 87, accidents just kept happening. And even after the software bug was found, AECL's first fix was, you're not going to believe this, they told users to just pry the up arrow keycap off the keyboard. It wasn't until the FDA had to step in and declare the machine defective that a full recall and redesign finally happened.
And you can just feel the sheer frustration in the FDA's response to that keycap idea. They wrote that the company's letter implies the inconvenience to operators outweighs the need to disable the key. Think about that. The regulator had to force the manufacturer to treat a lethal defect with the seriousness it actually demanded.
You know, the Therac-25 really proved that software isn't some abstract thing. It has real-world, physical consequences. This story comes from the dawn of the software age, but it leaves us with a question that feels chillingly modern. In a world that runs on billions of lines of code, in our cars, in our planes, in our medical devices, how many of them are all that's standing between us and the next disaster?